Yesterday, yeah, you enough? I'll take it home. Okay. All right. So yesterday we figured out the orbitals were places where they could go. We learned which orbitals are available. Now we just got to figure out what order they fill. And the general rule is you can't fill a bucket from the top down. The only way to fill a bucket is from the bottom up, right? And that's true with orbitals too. They fill lowest energy first, and then they go up from there. Like you fill a bucket from the bottom up, you fill these from lowest energy to highest energy. The only problem is that we get energy and energy level confused. Because to Bohr, they were the same. But now we're saying that energy level is about the waves. And those energy levels overlap each other. So they don't fill up in energy level order, they fill up in energy order. So I don't fill up the 1s, the 2s, the 3s, the 4s, the 5s, not in that order. And it makes sense because if you think about all those orbitals sitting on top of each other, they're going to interact with each other. Okay? There's going to have to be a change. So what we're going to do with those pink pieces of paper, we're going to come up with a counting system. Just keep track of how many electrons we have. And a box is an orbital. A box is a place for 2 electrons. So you'll see that on my diagram, I drew 1 box for S's, I drew 3 boxes for P's, 5 boxes for D's, and 7 boxes for F's. Let me see what I'm talking about on top of that diagram. Okay, so each box is an orbital shape, so each box is room for 2 electrons. Now, if you remember, what they said was Bohr could get the math to work for hydrogen, but he couldn't get it to work for anything else. And once you see what happens to the energy with the quantum mechanical model, you'll see why he couldn't get it to work with anything else. So this is what the energy diagram looks like for hydrogen. It's not the one on your paper. The one on your paper is different. Hydrogen, it doesn't matter where the electron is, it will never be repelled by another electron because there's only 1 electron. Okay? But as soon as I put that second electron in, I've got a whole new set of forces. Not only is the electron being attracted to the nucleus, it's also being repelled by the other electron, depending on where that other electron is. So what happens is my orbitals, because they overlap each other, they interfere in different ways. And this is what happens to the order. That's the diagram you've got on your book, in your paper right there. Okay? This diagram describes the order in which they're going to fill up. So if you look at it, if you work your way up, first you're going to fill up 1s. It's at the bottom. Then you're going to fill up 2s. It's next highest. Then you're going to fill up 2p. It's next highest. Then you're going to fill up 3s. Hey, we're doing 1, 2, 3. I thought you said it wasn't 1, 2, 3. Then I do 3p. Okay, but actually on your diagram, 4s is lower than 3d. So you fill up 4s before you fill up 3d. Then you fill up 3d. Then you fill up 4p. Then you fill up 5s, then 4d, then 5p. If you work your way up, those numbers don't go in order. You just have to follow this order on the way up. Okay? So there is actually, what we're talking about here is called an electron configuration. The word configuration means arrangement. So electron configuration is the arrangement of the electrons. Okay? And there are 3 rules that govern the order they fill up. Rule number 1, we've already talked about, we just didn't give it a name. Okay, lowest energy first, that is the Aufbau principle. Finally, something that's not somebody's name. Aufbau means building up in German. So it's the principle that they build up, that you can't start on the top floor of a skyscraper. Would be kind of hard to do, wouldn't it? Okay. So we've already talked about that. So this the diagram you have at the top of your page there, that diagram is called an Aufbau diagram, because that's the order they build up. Okay? You don't have to memorize the order. You have to be able to use the diagram to get there. Is that okay? And so the Aufbau principle gives us grief because of the overlap of those orbitals from different energy levels. So they got different levels overlapping with each other. I need a diagram to keep track of what's going on. Without a diagram, I don't know what's going on. So that overlap on the diagram causes some grief. We try to just, it's not all the ones, all the twos, and then all the threes. We got to go in the order that the diagram goes. Hey, second rule. We've already talked about the second rule too. We said every time we had an orbital, they had room for 2 electrons. That's called the Pauli exclusion principle. At most 2 electrons in an orbital. You can have 0, you can have 1, or you can have 2, you can't have 3. The hard part to explain is, why can you have 2? That's the hard part, not why only 2. The hard part is, how does the second one stick? Because if you've got a place for electrons, right? Electrons have the same charge. So if I'm trying to put 2 electrons in the same place, they're going to push each other away. They don't want to be in the same place. So there's got to be something else going on. So what they found was going on is kind of bizarre. Okay? They found that if you passed electrons through a magnetic field, half of the electrons had a magnetic field that pointed one direction, and the other half pointed the exact opposite direction. Okay? So if you shot this beam of electrons, it would divide into 2 based on its magnetic field. Half would go up and half would go down. Okay? And they had tried to explain, how come an electron behaves like a magnet? Now, all they knew about magnetism at the time was that that moving electricity gets you magnetism. So how can an electron act like a magnet? It's got the charge part, but that charge has to be moving. How could it move? Well, they said, here's how it could be moving. It could be spinning. And if it spun one way, the magnetic field would go one direction. And if it spun the other direction, the magnetic field would go the exact opposite direction. So if the magnet could spin in 2 different directions, then you would get the 2 different kinds of magnets. Okay? So they said the magnets, they must be spinning. And that's because they're acting like opposite magnets. What happens when you put opposite magnets together? They stick. So the reason why you can put the 2 in there is because they're acting like opposite magnets, and they're sticking a little bit in addition to being repelled. But there's a stick that makes them stay. They soon found out that electrons weren't really spinning. But that doesn't stop them from calling it spin. So their first idea was that it was spinning. Now they know it doesn't spin, but they still call it spin. Okay? So spin is just what kind of magnet it's acting like. The place that spin gets used is MRIs, magnetic resonance imaging. Okay? They're actually using the spin of hydrogen nuclei, the proton and hydrogen. That's what they're measuring. And that, when you've been in an MRI, it's really noisy. And what you're hearing, you hear this, and it goes, and it's noisy, you got to have earplugs. The table moves slowly. And what that noise is a magnet turning on and off. A really powerful magnet. Because if they turn a really powerful magnet on, they can force all the spins to go the same direction. So they force all the spins to go the same direction. And then they turn the magnet off. And half of them are going to switch back. And since they switched back, they gave away energy. Giving away energy means they gave off a wave. And they give off radio waves. And around the magnet, they got receivers to map where the radio waves come from. And that's how an MRI takes a picture of the inside of your body. It's actually taking pictures of all the hydrogen atoms. Okay? That's what it's getting, is where all the hydrogen atoms are, because every time it comes on, it forces them into a stable where they got two charges and two magnets that are the same. They're not stable. As soon as they turn it off, one's going back, and when it goes back, it's losing energy. So it's got to give that off as a wave. Just like when the electron falls down, it gives rid of its energy as a wave. When the line up, the spins switch back, they get a radio wave out, and they can see the inside of your body. So that's why you do not want to go into an MRI if you got any metal on you, because it will pull that metal from across the room, and if you happen to be between the metal and the magnet, you're in the way, and it will pull that thing through you. Okay? People with the wrong kind of tattoos have a problem. Got metal in your tattoo? Got metal in your tattoo, you don't want to get an MRI, because it's going to be yanking that metal around. It'll warm your arm up, give you a burn. You don't want to carry metal into a room with an MRI machine. It's a huge magnet. Okay. So that was more. It's called Hund's rule. And Hund's rule is that if occupy orbitals of equal energy, like the 3p orbitals, or the 5d orbitals, or the 7f orbitals, those all have the same energy. If they occupy ones of equal energy, they don't pair up until they have to. So analogies. The orbital is like a room. And it's a room for two. A whole bunch of orbitals put together is a whole bunch of rooms put together like a hotel. And a whole bunch of orbitals would be the electron cloud. I build a hotel by putting rooms together. I build an electron cloud by putting orbitals together. Every room has room for two. But if a family with two daughters rents 3 rooms, are the daughters going to share a room? No. Everybody's going to want their own room, right? Well, it's the same thing that happens here. The electrons don't want to have a partner if they can avoid it. So if there's a room on the same floor, they're going to take the other room before they pair up. Okay? So those are all the rules. Now let's use that diagram and figure out the electron configuration of phosphorus. Where can you find all the electrons in a phosphorus atom? How are the electrons arranged in a phosphorus atom? The first thing we need to know is how many electrons we have to describe. So how many electrons does phosphorus have? Look up on the periodic table. It's number 15. So it's got 15 electrons. Everybody okay with where I got 15 from? Hey, that's probably why we learned it last unit, was so we could do stuff like this. Okay? 15 electrons. So, to my diagram, I have to count up to 15. Okay, so where do I start? At the bottom. Okay, they put the electrons in as arrows. And by convention, to indicate the spin, up spin or down spin. By convention, they always put the first one in up and the second one in down. They don't know, and it doesn't matter. But it's easier to read the diagram if you put the first one in up and the second one in down. So I put in 1. Can I put a third one there? No, the Pauli exclusion principle says at most 2 electrons per orbital. Those opposite spins would attract a little bit, but if I tried to put a third one, it wouldn't be attracted or repelled anymore. It would be repelled more, not attracted anymore. So the third one won't fit. Okay, so where are the next electrons going? Okay. I got to keep track. They went to 1s, opposite spins. Then next ones are going to 2s. And there's 2. So I've got, I was going to 15, I got 11 more to go. Working our way up. Where's the next ones go? 2p. So I got to fill up 2. I'm going to fill up 2p with 11 into a 2p. Put in 11. So this 2p is going to get filled up, isn't it? So put 2 5. And that's 10, so we got 5 more to go. So where do the next ones go? 3s, and there's room for 2 there. 3 more to go. Where are they going? 3p. Am I going to fill 3p up? No, there's room for 6. I'm going to go and put in 3. So now is where I got to worry about Hund's rule. When I put them in, first one goes in the first box, other third box. If 3 people, so this phosphorus, one of the reasons it behaves the way it does is because so the only way to tell if it's got paired electrons is to look at the very end. Because everything that's full is going to be paired automatically. But that last orbital may not be full. And if it's not full, it may not be paired. Make sense? See 3 unpaired electrons? Now, that's where the electrons are. Do you think scientists draw this picture every time? So if they want to talk to each other, they'd have to say the first energy level's s orbital has 2 electrons. The second energy level's s orbital has 2 electrons. The second energy level's p orbital has 6 electrons. The third energy level's s orbital has 2 electrons. And the third energy level's p orbital has 6 electrons. That's a lot to write, isn't it? But they shorten it down by writing it like this. 1s2. First energy level's s orbital has 2 electrons. 2s2. The second energy level's s orbital has 2 electrons. 2p6. The second energy level's p orbital has 6 electrons. 3s2. The third energy level's s orbital has 2 electrons. 3p3. The third energy level's p orbital has 3 electrons. So this is a lot faster to say. 1s2, 2s2, 2p6, 3s2, 3p3. And that's how you build an electron cloud. The electron cloud for phosphorus has 1s, 2 electrons close to the nucleus in the sphere-shaped region. Then 2s, 2 more electrons in the sphere-shaped region a little bit further out. Then 2p, 2 electrons this direction, 2 electrons this direction, 2 electrons that direction. Then 3s, a bigger sphere with 2 more electrons. And then a bigger set of dumbbells, one this way, one this way, one that way. And that's where you find all the electrons in phosphorus. Let's try an iron-on. Right, the electron configuration for iron. Hardest. How many electrons do I get? Hardest part is finding iron on the table. It's Fe. It's number 26. So since it's number 26, I got to talk about 26 electrons. So I got to work my way up to 26. So I start at the bottom and fill up the 1s. So I got 1s2. Then I work my way up. 2s2. That's 4 of my 26. Next ones are going to go to 2p. 1, 2, 3, 4, 5, 6. So 2p6. And then 3s can hold 2. That's 12, almost halfway there. Then 3p can hold 6 more. So that's 3p6. That's 18. I'm just adding up the numbers on top. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18. Then next I go to 4s, and I got room for 2 there. That's 20. And now I hit 3D before I hit 4p. So next one I fill up is 3D, not 4p. They go in energy order, not energy level order. Okay. So I'm going to put 6 into 3D. Am I going to fill it up? No, so I should do one at a time and then pair up, right? So that would be 1, 2, 3, 4, 5, 6. So that would be 3d6. So as long as you got the diagram, you're just working your way up. Does that make sense? Work your way up. Now, that diagram's a pain. All you have to do is memorize that order. Nah, you don't have to memorize that order. Because there's an easier way to remember. The diagram at the bottom of your page. If you follow those arrows, it will go in exactly the same order as that off-bow diagram. If you start at the bottom and follow the diagonal lines up, it gives you the order they're going to fill up. So first is going to fill up 1s. 1s can hold 2. Then the next line goes through 2s. All right? So that 2s can hold 2. The next line is going to hit 2p, and then it's going to hit 3s. All right? So that's going to be 2p6. P's can hold 6. 3s2. S's can hold 2. Next line is going to go through 3p, then 4s. Then 3d, 4p, 5s. I'm just following the diagonal lines up. And see what this does? See how it did what we did with iron right there? It filled up the 4s before the 3d. It gets the energy levels in the right order. So it's just a trick for recreating that first table without having to memorize it. How do I know you don't have to memorize it? Because you've been staring at it all year. Right above my head. I'm not taking it down. It'll always be there. Follow the diagonal lines. Okay. The next line will go through 4D, then 5P, then 6S. Notice, it doesn't matter, I can stop and talk about something else, but I know where the next one's going. Where's that next diagonal line going to go through? 4F, 5D, 6P, 7S. And the next arrow is going to go through 5F, 6D, and 7P. And I stopped my table there because I hit 118. And 118 electrons is the biggest atom on your periodic table. It's number 118. So I don't have to go any further until they make the next heavier atom, number 119. Where's it going to go? Where's the electron for 119 going to go? Now, you're tempted to write 6F, but the right answer is 8S. I didn't put 8S down there simply because I didn't need it. But that next arrow points towards it, doesn't it? So number 118, number 119, and number 120 are going into 8S. Where's 121 going? So you say, ooh, I want it on that arrow, but look at the pattern. There's got to be an orbital here. I just didn't write it before because I don't need it. But it's going to be a 5G. And a G is going to be 9 shapes with 18 electrons. Right? Just doing the odds. 1, 3, 5, 7. Next one's 9. Okay? So we don't need the 5G or the 8S until they make more elements. But those orbitals are still there. Those are places the electrons can jump up into. All we're showing is the occupied orbitals. When they're heated, they jump to unoccupied orbitals and fall back down, and we get to see the light. That's how we know these things are here, is because we can see the jump between those two. Okay. Now, this is the order we just went through. Okay. Your book does something bizarre every once in a while, and I don't want you to be surprised by it. After you've done all that, they regroup. And they regroup and put all the energy levels together. So all the 1s, all the 2s, all the 3s, all the 4s, all the 5s, and all the 6s, and the 7s. So they put all the 2s together, so you got 2s, 2p. So they move the 4s from right here to there. All right, so you have 4s, then 3d, up here. They move that 4s over there. Just put all the 4s together. Then they put all the 5s together. And they put all the 6s together. And they put all the 7s together. So your book will write it 2 different ways. I hate this way, but you're going to see it because it's in your book. You'll lose information when you do it that way. Important information. But your book makes you do it anyway. I prefer this way. If you do it either way, I'm okay with it. But I don't like the rearranging. So I'm not going to require you to rearrange it. I just want you to be aware of when you look at it, it might have been rearranged. So let's try a few. Let's write the electron configuration of boron. Boron's number 5. So I have to describe where 5 electrons are. And we can just follow the diagonal lines up the bottom. So the first line goes through 1s. So I write 1s. S's can hold 2. 1s2. I have described 2 electrons. Am I done yet? No. Next line goes through 2s. How many can s's hold? 2. Am I done yet? No. Next line goes through 2p. 2p can hold 6. Do I write a 6 here? No, because I only need 1 more. So it's 2p1. We would have got the same answer if we'd used the diagram. Look at the diagram. You've done 1s, you would have done 2s, and you would put 1 line in the 2p column. Right? So it's the same stuff. Just different ways of representing the same information. Let's try selenium. Selenium, number 34. So let's get used to using the diagonal diagram, because I'm not going to print the off-bout diagram on the table. I will print the diagonal one. Eventually you'll learn that you don't need that there's even a better place to look. Okay, my first one's going to go through 1s, and I'm going to hold 2. Next arrow is going to go through 2s. It'll hold 2. Next arrow is going to go through 2p, and 2p can hold 6. Should I fill it up? Yeah, because that 6 only gives me 10 of my 34. 2, 2, and 6. Then after 2p, notice I can stop and talk, because all I can do is say, oh, I was here at 2p, next I'm going to 3s. And 3s can hold 2. Next arrow, 3p. And p's can hold 6. That gets me to 18. After 3p is 4s. 4s can hold 2. That's 20. And then, next arrow, 3d. Am I going to fill it up? Yeah, because I got 14 to go, and d's can only hold 10. And then after 3d comes 4p. I'm going to fill it up. Now, because I'm at 30, I want to go to 34. So I only need 4. So that's right there. So the electron configuration of selenium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2, 3d10, 4p4. Isn't that a lot easier than saying the first energy level's s orbital has 2 electrons in it? Isn't it easier than drawing arrows? Okay. I mean, because what happens if you imagine what the diagram would look like if you asked to do hafnium? Number 72. You want to follow that diagram all the way up to 72? That's a lot of arrows. That's 72 arrows. I don't want to draw 72 arrows. I'll just follow the arrows on the way up. And I can go pretty fast because I've done these first few a couple times. I know it's going to be more than 1s2. I know that it's going to be more than 2s2. I know that I'm going to fill up 2p and 3s because I just went to 34, right? So I should be able to go pretty fast because I don't have to count until I get big. Right? We stopped at 4p, right? And we were at 34, so I can go through 4p right away. So what comes after 3s is 3p. 3p can hold 6. And 4s could hold 2. Next arrow. 3d can hold 10. And 4p could hold 6, and now I'm at 36. Now I got to get count again, but I'm halfway done. What comes after 4p is 5s. So that was 36, 38. 4d is 10. There's 48. After 4d comes 5p. That's 6, that's 54. Then 6s is 2, that's 56. Oop, got another arrow. Oh, and it goes through f's. So 4f, and how much can f's hold? F's can hold 14, right? 7 shapes. 14, that's 70. And then after 4f's comes 5d. And I could put 10 in it, but that would give me 80. I only want 2, so I end up at 72. Just follow the arrows up from the bottom. Make sense? And that describes where you're going to find all 72 electrons in hafnium. This is what the electron cloud for hafnium looks like. It's built up in layers that overlap each other. Okay? The S's, you got 6 different layers of spheres. Small, bigger, 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 bigger. You got 4 different layers of P's. Small barbells, biggest barbells, or bigger barbells, biggest and biggest plus. Right? You have 2 sets of D's. and one set of Fs. Okay? All of those laying on top of each other. And that's what makes the electron cloud for selenium. Okay? So that's half of the reading guide that you'll read over the weekend. The first half. A couple more details. This is the last skills we're going to learn before the test. So start thinking about that test. And I will see you on Monday, where we'll practice some of this.